Alright, this is Quiz 2 from 2015, Unit 2, Quiz 2. What kind of molecules are detected in mass spec? Be specific. What is the base peak? Cations are always detected, the plus charge things. Base peak is the most stable and prevalent fragment in mass spec. Right? That probably come from a tertiary carbocation or something like that. Here's a tricky one. Draw the least likely fragment pieces, least likely from the molecular ion below. Just show the breakage of one bond. Numbering helps. So in this case, least likely means you'd want to form primary things, specifically primary carbocation. So if you broke between 3 and 4, either way you break, if you put the dot on 3 or put the dot on 4, you'd have to put the plus charge on one of the other ones. That would leave you with a primary carbocation. So this would be the worst breakage. There's other places you could break and make primary carbocations, but this would be the worst. Right? So the worst is because you form primary carbocations in either C4 or C3. You'll always have it. And remember, primary carbocations only have 3 hybrid conjugation buddies, right? So if you hit the carbocation here, there's from 1, 2, there's one sigma bond away, 1, 2, another sigma bond, and then there's an H. So a primary only has 3 hybrid conjugation buddies. So that's not very helpful. More the better. This one, draw the molecular ion for the molecule below, including all electrons. Show the mechanism of curved arrows and fragment product of the alpha cleavage. So in this case, first thing first, knock an electron out. 3 arrows show that alpha cleavage. Right, we're breaking this bond here between the alpha and the beta carbon. Electron comes down from a new pi bond. Electron goes to the beta. From a radical and a plus charge cation, this is what you see. This is a molecular ion. This is what you see in this case. Label 3 important frequencies for the IR in the spectrum below. Don't forget, here's your molecule. So in this case, we have an alkyne. It has an sp, a sharp sp CH stretch, hybridized CH stretch, an sp3 hybridized CH stretch. It also has the CC triple bond stretch. There's other ones possible. There's some other things you could think about, the methyl group out here and things of that nature, but those are the 3 major ones. Alright, for this question, ask what type of electromagnetic radiation is used in NMR. What information does this tell us? And just give one example. So radio waves are used in NMR. And there's at least 3 things you knew at this point. Now there's 4. The different types of H's it tells us. If they're near electronegative element or feel the radio waves, that's a shielded or deshielded. The relative ratio, right? The area beneath the peaks. So if there's 3 to 2 ratio of protons in a molecule. And the 4th one, which is not included here, but we learned later on, was if H's are near each other and they split and they're coupled to each other. For this other one, number 6, which carbonyl below would you predict to have such a higher wave number or higher frequency? People confuse this, right? Wave numbers for IR, right? We're talking about IR and Y. So in this case, a higher wave number would be at a higher frequency. So if you can do resonance with this molecule, right? So it shows some resonance structures. That gives this cetyl bond O some single bond character, which means it's a longer bond then, which become at a lower frequency. So resonance in this case gives the conjugated ketone some single bond character, which would make it have a lower frequency. Therefore, this one without conjugation would have a higher frequency or higher wave number, right? Wave numbers for IR. Good here. Simply put, we wanted you to draw in all the hydrogens, the molecules below, indicate the chemically non-equivalent hydrogens. Drawing the H's in should be pretty simple, right? Carbon wants 4 bonds. A lot of people miss this H here. So some people try to put some H's on carbons with already 4 bonds. Be careful there. So this one has 4 types, 1, 2, 3, and 4. Notice the symmetry in the benzene ring here. Again, this has 5 types. A lot of people miss this H. So 1, these are both the same. 2, 3, 4, and 5. 5 types. For the bonus here, so a ring flip is not possible because this big tert butyl group cannot be axial. So it has to be equatorial, so all of these are the same, A. That means all the equatorials and axials are going to be different because we can't do a ring flip. So B is different, and then every carbon, since there is some symmetry here, right? The D's are both axial. C's equatorial be different. These C's are the same, be different than the D's that are axial. One carbon over, again, the axials, which we call an E here, be different than the equatorials, which we call an F. And then the last carbon, both the axial, or both the equatorial here and the axial will be different as well, so it'll be 8 total types.